our class logistics. Okay, there's still a little bit confusion, so let's see if we clear it up today. We're running a little bit late on the lab. I think the Michigan guys are doing something to us. Okay, so we're running a little bit late on the lab. Okay, so the lab one was due a few days, right, into the weekend. So lab 2 originally was going to be due today, but we released it about 4 days ago, right? 2 days ago or 4 days? 3 days ago. Okay, 3 days ago. And so we're going to make it due sometime this weekend. Okay, so try to finish. And we're going to gradually try to bring the due date back into the original schedule. Okay, just so that everyone is okay. And in terms of the quiz is going to be released hopefully today. And that quiz, you have a whole week to do the quiz. So whenever we release a quiz, you have 1 week. Okay, you can try multiple times and you can study a little bit after you take the first one, right? So that's what it is. Okay, so these days are release days for the quiz. Okay, so does that clarify lab, quiz? Right? Okay, yes?
So you said the lab 2 will be due sometime this weekend?
Yeah, we're trying to get it due maybe Sunday night or maybe Monday. So we'll see how things go. Okay. So but you were able to do the submission now, right? Yeah. So it should be it should be okay. Lab 2 it shouldn't be too hard, and you have some of you have some memory access issues, but it shouldn't be too hard. If it's too hard, you should be talking to to TA or me. Okay. Okay. Any other questions before we go into binding? No? Okay. Very good. One bonus point if you could tell me how to fix the microphone. All right. Okay. So what we're going to talk about is binning or spatial sorting. And this is a very important technique for parallel programs to be able to have what we call the data scalability. Okay, and we're going to go into data scalability and then talk about why it's a problem mostly for gather-based algorithms. And the gather-based algorithms are used in many domains. Okay, we talk about gathering for electrical, the potential calculation. But if you look at ray tracing, if you look at in video games, how they detect where the bullets go and how many which person gets hit or which object gets blown up by the rocket launcher and so on. A lot of these things are calculated with gather-based algorithms. And one of the biggest problems with gather-based algorithms is that every thread needs to have some way to determine where to look for input. And the most naive approach is that we can just have every thread to look at every input, but then when the input gets really big, then every thread will be doing a whole lot of work for no good outcome, right? So the binning approach is really to give you the ability to be able to have every thread to be able to have a limited scope of inspection. Okay, and it turns out that this is there's a whole range of techniques that people have for different types of data distribution. Okay, so we're going to go over the most basic one today, and the most basic one is what we call the uniform binning. And it has some very desirable properties, but it also has some shortcomings. and then I'll point to how you can do the next level. And I think we'll circle back and talk about the more dynamic techniques after we talk about the dynamic refinement. So there's quite a few trade-offs when we do input binning, and the especially if we do uniform binning, we actually have several big dimensions that we need to optimize for each application. So those are the things that I'm going to talk about today. Okay? So let's go to scatter and gather transformation. So this is a slide that you already have seen from lecture 2, right? So we convert from scatter, where every thread scatters the effect on behalf of one input, right? Into these, scatter the effects. So then you have these conflicting updates to the output by different threads. That's why we need to do atomic operation. And atomic operation serializes the threads involved whenever they have a conflict, right? So that's where the inefficiency comes from. And we convert that to gather so that every thread is going to be collecting the input values for generating the output. So obviously the amount of work that every thread does depends on how many inputs that thread has to examine, right? That's the fundamental definition of the work done by every thread in a gathered computation. The problem is the inputs tend to be much less regular than the output. Okay, so if you look at the electrical potential calculation, the inputs are the atoms. Okay, and the atoms are scattered around in the space. The output is the grid, right? The grid is a very regular, artificial, designed, equally spaced points in the space, extremely regular. So whenever you have a scatter algorithm, it's actually really easy to write that code because you just take each input atom, line up the input item, take each input atom, and then you can scatter the result to the spatial points by just calculating the coordinates, and then you're done, right? But whenever you have an output grid point, and you say, I want to go and gather all the input atoms that are relevant to this point, then I need to somehow search through the atoms, but the atoms are scattered around in the space. There's not a very easy way to isolate the relevant atoms unless you do something. And so we're going to do something now. Okay, we're doing this pre-sorting, sometimes we call spatial sorting, sometimes we call binning, in order to give us that ability to be able to quickly identify the subset of inputs that are relevant to the output point, to each output point, so that every thread can quickly zoom into the subset of data that it's supposed to look at. And so basically, we want to be able to for each thread to efficiently locate and gather all the inputs relevant to its output, or even more importantly, to efficiently exclude all the inputs irrelevant to its output, because that's where the computational efficiency is going to be. The more we can exclude wasted work, we can exclude the atoms that are not going to affect the grid point, the more efficient the algorithms. In a naive arrangement, all the threads may have to process all the inputs to decide if each input is relevant to its output. A very easy way to, the naive way to do something is you take every thread looks at every input, and then most of the threads say, oh, it doesn't do anything for me, right? But that is already contributing to the work done by the threads. So just the fact that you need to inspect all the input already increase your computational complexity. So this is one of the things that many people ignored early on in parallel computing. A lot of people essentially ignore the computational complexity of the algorithms. They say, oh, if I have a parallel algorithm, I can afford to have higher computational complexity. The problem is when you have a higher computational complexity algorithm, the sheer amount of work is going to overwhelm the hardware that you have, and you invariably will end up with slowdown. if you're not careful. And we're going to actually go into this quite a bit. So, this makes the execution time scale poorly with the data set size, and this is what we call the data scalability problem. Especially a problem with Manycore design is we are trying to process large data sets, right? A very important application is that we want to be able to process very large data set with these parallel computing resources. So, for example, the reason why GPU has been so popular is because people want to use GPUs to train on very large, input, data sets, right, for training neural nets. So, if you don't have a large number of, input images that you want to train or the, text data that you want to train, you don't need to use GPUs, right? So, but when you have a large data set and then, your computation scales very poorly with the size of your data, then you start to run into trouble, and as we will see in the next few curves. So here is the review of the electrostatic potential calculation problem. We have all these grid points, right? So these are the regular grid points that we define in the space, and then we have these atoms in the that are somewhat distributed in the space. So at each grid point, we're calculating the sum of electrostatic potential contribution from all the atoms, right? And all threads will read all the atoms in your MP. When you do your MP, we're doing what we call the direct Coulombic summation algorithm, assuming that all the atoms are going to have effect on all the grid points. In reality, it's true, because no matter how far the atom is, there will be some level, right? Some level of contribution. But in practice, that's not what we do. We can, if we do that, then this becomes a quadratic complexity algorithm, meaning that the number of grid points and the computation that we need to do is the number of grid points, right? The number of grid points times the number of atoms. Because for every grid point, we need to process all the atoms. So the total amount of work is going to be the total number of grid points times the total number of atoms. And why is it quadratic? Because when the volume becomes bigger, right? When you think about it, when the volume becomes bigger, then the number of grid points becomes bigger, right? So the number of grid points is proportional to the volume, right? And the number of atoms in your solvent or whatever in your space also is proportional to the volume. So when you increase the volume of your experiment or your simulation, you have quadratic effect of the amount of work quadratically proportional to the volume. So that's why when we try to use a bigger machine to simulate a bigger volume, we will begin to have quadratic increase of amount of work. So the algorithm complexity, if you look at linear algorithm and n log n algorithms, they will increase somewhat slowly until it gets really big, and then the quadratic. So this is classical, right? This is classical. You learn this in 374, right? Data structure in algorithms, and this complexity is actually really, really scary, because when you increase let's say this is the volume that you're trying to simulate, and as you increase the volume, the amount of work that is going to be involved can grow so fast that even if you use 100 times parallelism, 1,000 times parallelism, at some point you'll be defeated. Okay, so that's why we no matter how parallel our machines are, the first thing we do when we run this very large data set is still to look at how we can control the complexity, the computational complexity of our algorithms. Okay, so in general, any algorithm complexity higher than linear is not data scalable. And a few years ago, the hot term is what? Big data, right? And so the industry was hit by big data about 15 years ago. And it was actually quite interesting. That was the rise of Facebook and several social media companies. And so the interesting part is these people came from Harvard and so on. They didn't go to Illinois, so they didn't fully understand algorithm complexity. So when they wrote some of the early software for these social media companies, they wrote these things in naive, quadratic algorithms. When they sort, when they do things, they don't do the real merge sort and so on. And in terms of log and log n complexity. So a lot of their internal implementations use quadratic algorithms. And as their user base grow, they start to see their system go slower and slower very, very quickly. So that's when the industry started to realize big data is a problem. It's a problem because when your data becomes big enough, then that's when the order, the big O of your algorithm start to matter. And let's say if your big O increased by 1 billion times, okay, so let's say your user base grew from 10 people to, let's say, 1 billion people, okay, and so that's 100 million, okay, and then you take 1,000 times parallelism. It's peanuts compared to 100 million. So that's why when your computation becomes, just amazingly big, it doesn't matter how parallel your machine is, you're going to have a very slow computation. Okay. So then most people realized that, so they went back to 374, and then they learned from Illinois classes. And then they say, oh yeah, n log n sorting, so that's great, so TerraSort, that's where TerraSort, algorithm came in, and then a few other things. So now the social media, they do spatial sorting and so on their, on their network, connection, things, and we're actually going to go into a few of those, in the middle of the semester. So then they start to get the data scalability somewhat under control. Okay, and here we have exactly the same thing. Let's say quadratic is ridiculous. So let's just say we figure out that we can do n log n, right? N log n is great, right? In fact I would say 90% of the 374 is about n log n algorithms. Okay, that's my simplified view of that course. One of these days I'm going to teach it, just to make sure that I really know what I'm talking about. So, but log n could be still scary because if you're processing 1 million data elements, n log n, that log n still gives you 20 times. So 1 million is not a very big number in terms of data set. Okay, 1 million data elements is nothing these days. We're talking billions and trillions of data elements. When you take that log, 1 million is 20 times, right? And then the billion is 29 times. And that kind of, even though it grows much slower than n squared, it still requires 20 more times of resource just to be able to break even, right? So if you have a linear algorithm for sequential, and then you parallelize it, but you have to use n log n to be able to parallelize it. You have to have at least 20 times more resources if you want to process 1 million elements, right? And that can be a very big hole to dig out of when you when you apply that to real world problems. So processing large data set is the major motivation for parallel computing, and if we cannot control that complexity, a sequential algorithm with linear data scalability could ultimately outperform n log n parallel algorithms. So that's why we need to be really, really careful. So this was actually a curve similar to a curve that some of the Berkeley people showed many, many years ago. There was an article about how you can lie with your parallel computing work. Okay, this was a classical paper in the high performance computing domain, and then this is essentially what these people are showing. They're showing that many people who published parallel algorithms in the early days ignored the computational complexity So essentially, they are blowing up the computation complexity to enable parallel computing, and then they will publish results in this kind of range. So they will just say, okay, you know what, for data size of this to this, look, you know, my parallel computing reduce the computation time and have a speed up. And then, but if you start to get bigger and bigger data size, then you start to have this problem. Okay, so then it gets reversed. It's a very well-known, you know, the phenomenon in the HPC community today. So everyone will ask you, you know, what's the complexity of the algorithm when you parallelize it. And so this is a real measured data based on one of the earlier GPUs, but it's still in general true in most of the GPUs today. So basically, you know, if we take if we just take that direct Coulombic summation, and you know we you know parallelize it, and you know so then we will get this quadratic you know curve, and then if we take the CPU. Okay, and take the CPU and do a sequential algorithm and only do a, you know, just a direct computation. So, you know, and then we'll do a cutoff, right? We'll do a cutoff kind of, you know, say for every, you know, atom, I'm going to only, you know, scatter to the grid points that are within a particular distance. After that, we will use what we call the long range approximation. Then you have you know a CPU like this. At some point, the sequential algorithm, because the sequential algorithm doesn't care about that scatter. Okay, so you know at some point the sequential algorithm will have shorter execution time compared to your parallel algorithm that have to look at all the atoms. So these are the spatially sorted you know algorithms, parallel algorithms. So that's why if you use the spatially sorted parallel algorithms, you will continue to have execution benefits over the CPU's you know the sequential algorithm as the data scale. So this is what we're going to be talking about today. So let's first talk about cutoff. Electrostatic potentials with the cutoff is is commonly used in almost all the simulation software because of the data scalability problem. Okay, so basically we say that whenever we have a atom, the atom can only have significant effect on the grid points when the grid point is within about 12 angstrom, okay? About 12 angstrom away or less from the atom. So for any other grid points, it will be, the effect will be very weak, okay? And you can use some kind of, approximation such as multi-level, the fast multiple methods to do the approximation. So that will go into the kind of the longer range calculation. So almost all these algorithms use short range calculation for the most significant contributions that atoms are making, and then use a longer range approximation for the effect of these atoms on far away the grid points. So if you look at the number of atoms, typical number of atoms within the cutoff distance. The cutoff distance in this case is 12 angstrom. Okay, and so it's roughly constant. That is, if you essentially you draw a sphere. Okay, you draw a sphere around any of these grid points, right? So you take this grid point, or you take this grid point, you draw a sphere. That sphere has a radius, right? Has a radius of about 12 angstrom. So you have a volume, right? That sphere defines a volume. And then for a typical chemistry experiment, that volume will contain about 200 to 700 atoms. Okay, that's the, it obviously depends on the density, right, of your material and so on. But it takes, in general, it will contain about 200 to 700 atoms for that cutoff sphere. And so what that means is that for short range force calculation, potential calculation, every grid point would be looking at approximately 700, atoms, right? So that gives you a constant amount of work for every grid point, right? And then suddenly your total computation becomes a linear computation with a factor of about 700, right? With about a coefficient of about 700, a linear algorithm, linear to the volume of your simulation. So this is exactly how VMD and NAMD, the big simulators running on supercomputers today, that's how they scale their experiments. That's why they can run simulation on some very realistic chemical experiment. If you think about it, a little beaker, okay, a beaker is actually a very large number of angstrom, okay, fairly large number of angstrom. So the grid points involving, just kind of shaking a beaker experiment is going to be a fairly big volume in terms of number of angstroms, right? So that's why, the typical grid point is about half of angstrom. And then you have about 12 angstrom of cutout distance, and so every grid point, when you do a round of calculation, the thread probably need to look at about 700 of these atoms and make that calculation. Okay, so this is a high level intuition. Okay, we want to have a method for every grid point, for every thread that is calculating the grid point, to be able to quickly zoom into the 700 or so atoms, okay, that the thread should be looking at, right? And this guy and this guy will be looking at different 700 atoms. So we need to organize our data structure so that all these grid points, and the threads calculating those grid points, will be able to quickly go into the 700 or so relevant ones for each of these grid points. Any questions before we go into the details? Because this is a very important intuition that will take you through the next few steps. Okay. Any questions? No? Okay, very, very good. So, the way that, for this particular one, you have this cutoff summation. And so the physics usually gives you this part. So the effect of an atom on a particular grid point is proportional to its charge, right? When the atom has bigger charge, it has more electrical effect, right? But it's inversely proportional to the distance between the atom and the grid point, right? So this is all very intuitive, and these are the constant, the coefficient or constants, for the electricity, electrical formulation, right? So this is all very, very easy. But then, when you do the simulation with a short range and long range force calculation, we oftentimes need to have this smoothing factor. Okay, this is what they call the smoothing factor. And the smoothing factor is 0 when you are outside that sphere. Okay, so it's 0 outside the sphere. But the tricky part is that when you're inside the sphere, it should be 1 for a long, long time until you're reasonably close to the boundary of that sphere. The reason is you need to have a smooth transition. If you have a method where all the atoms, all the grid points that are within, all the atoms that are within the sphere will be exactly 1, and all the atoms that are outside the sphere are exactly 0, then you have a very abrupt choice. Okay, and I get this, if you want to relate to this, this is what I get, teaching undergraduate students all the time. Professor, I'm only 0.03 away from a cutoff of A. Why should I get A minus? Right? Have you heard that before? You probably have said that before, right? So we have a smoothing function. So basically, when we grade, we have these cutoffs, and then we look at the one to the right a little bit, and then say, oh yeah, this is close enough. Okay, let's just promote a few. So that's the smoothing function. Okay, so that we don't have this very abrupt cutoff. And in physics, this is the smoothing function is that if you have everything on one side to be 1 and the other side to be 0, you start to introduce the kind of the step function, and when you take any kind of transformation like Fourier transform and so on, you start to have a very high frequency component in your simulation that it may not converge. Okay, so that's why. By the way, that's 210. Okay, so go back and review 210. Fourier, Laplace, okay? There's a good reason why we teach you all that stuff. And in the long run, they're still helpful, okay? Occasionally, I still need to go back to my Laplace and then figure out, some of the stuff with my science teams. So, okay, 210 is actually pretty useful. So that's why we have the smoothing function here. And, it's the ratio of R over RC. This is the cutoff, right? So this ratio, when R is much smaller than RC, this term becomes extremely small, right? It's a square of that ratio. So let's say if it is half the distance, then this is, this becomes quarter, right? So it emphasizes it kind of emphasizes sort of, whenever you're a little bit away from that cutoff distance, this ratio becomes very small, so that 1 minus this becomes very close to 1. And then you take the square to further emphasize that effect, okay? So that most of the contributions, sort of, when you get to close to the sphere, that's where this becomes very significantly deviating from 1, and then it will kind of drop down to 0 in a smooth but fairly fast way. Okay, so this is what smoothing function is about. So that's why when you look at the real scientific code, oftentimes you look at this and say, wait a minute, it's not exactly the physics formula that I know, because it's not just the physics differential equation or the Maxwell equation terms. They also added some of these smoothing functions and so on. If you don't understand why they did it, the code is almost impossible to understand. Okay? Now, that's not the main point of the course, but on the other hand, there are a few things that I learned over the years that I feel that if you are interested in parallel computing, ultimately, you will, at some point, you're going to run into some kind of code that's from the domain, and then you will see some of these kind of, the approximation methods, and then, that you need to understand where some of these terms come from. Now, so what is the implementation challenge? So for each tile of these grid points, okay, so, remember we have, we want to be able to use a thread block to calculate the potential value for like a tile of grid points, right? So for these grid points, we need to identify the set of atoms that are needed, that need to be examined. And one could naively examine all the atoms and only use the ones whose distance is within the given range. But the problem is, again, that gives you the high computational complexity. So, so that's why, each thread need to avoid examining the atoms outside the range of its grid points. So this goes into binning or spatial sorting. It's a process that groups data to form a chunk called bin. Okay, so we're going to take the data, the atoms, and we're going to begin to bundle these atoms together. The atoms that are physically close to each other, we're going to bundle them into a bundle called a bin. Okay, so this is, in many ways, you can think about it as data coarsening. Okay. And whenever we access any data in that bin, we access the whole bin. We can access all the data in that bin. So that whole bin gets accessed together. Okay? They're all in, they're all out for each computation. So each bin collectively represents a property of data in the bin. So this helps the problem solving because of data coarsening, and we can have uniform data arrays, variable data arrays, or KD trees, or arc trees, and so on. And you probably have heard some of these terms in the past. So in the uniform part, the bin, what we do is we partition the space uniformly. Okay, we take the space, we cut the space in a uniform way. So each partition is of uniform size. And then, because the atoms are distributed in the space, some of the bins may have more atoms than others. Okay, so that's one way to do it. The other extreme is to say we absolutely want the number of atoms in each bin to be the same, right? We are willing to change the size of these bins, but we want the number of atoms in each bin to be nearly identical. So that gives us the spatial trees, because the way that we partition is that we're going to take the atoms, and then we're going to try to draw a line, okay, to cut the space into two halves, and each half will have the same number of atoms. So if you have a very, very dense part, have the part of distribution and a very light part distribution, the cutoff point will be close to the middle of that dense part, and then you have a bigger part, half for one bin, and then you have a smaller half on the other bin. But the number of atoms will be similar. And then you do another cut across these two halves, and then you generate 4, right? So that's how these spatial trees are generated. And that process is also spatial sorting. So if we do uniform bins, the generation of these bins and assigning the atoms to these bins is a lot easier than if we try to generate non-uniform bins but spatial trees that give you, very balanced number. All the games pretty much use trees, okay? Because the games, the most important usage of spatial sorting in games, I'm talking about computer games, is that you have these scenes, right? You have scenes, and you have soldiers, you have the vehicles and so on, and you have these machine guns that are shooting, right? So the scene may have a part that has very few things, and then you have a part that is full of objects. So they do the spatial sorting to essentially give you the same number, okay, a relatively uniform number of objects in each of these partitions, so that when you shoot a bullet, that bullet is going to essentially pick out only the partitions that are going to be intersecting the course of that bullet, and then you only look at the objects of the partitions that intersect. So this is exactly what I mean by data coarsening. Every partition, all the data points in one partition that intersects with that bullet will all be examined, okay? And so that's why you're going to it's important to partition in a way that you don't look too many. So you want to refine your partition so that every time you examine a bin, you will be looking at a reasonable number, right? And the way to think about it is like if you degenerate to a single partition, right, then you're looking at every data point, right? So you want to get as many partitions as you can in order to be able to save your computation. So let's start with the most basic one, okay, the uniform binning. So we divide the simulation volume into non-overlapping uniform cubes. So this is a simulation volume with some atoms. So in this case, we partition the volume into 8 points, 8 partitions, right? 1, 2, 3, 4, 1, 2, 3, 4. So we partition this into 8 uniformly sized bins. Size means physical size. We're modeling that physical size. So each bin models the same physical size, space in the simulation. So So there will be grid points in each bin, and there will be atoms in each bin. Right? So every atom in the simulation volume falls into a cube, based on its spatial location. So this atom here falls into that cube there, and then this atom falls into this cube here, right? So some of the cubes may have 2 atoms, right? Some of the cubes may not have any atom like this, right? So that's that would go through a single pass to attribute each atom into one of these bins. In practice, each bin is a small array. Okay, so we allocate memory, and we have a small array allocated for each bin, and then when we go through the atoms and say, according to the coordinate, is this atom, which bin covers this particular atom in the simulation, and then we assign the charge and the 3 coordinates of the atom into that small array. Okay, and so if we have multiple of these atoms, that array will have multiple useful elements, but in this kind of, but we also may not have a full bin. That is, the bin may not have the full capacity used. For example, if you have an empty bin, then we'll have all what we call the dummy elements. Those elements are all of 0 charge, right? These elements will not contribute to any of the grid points if you look at it, right? So for this computation, as long as we set the charge to be 0, even if you process them, they will not add any value to the electrical potential. Okay. So here, so we pre-sort these items into the bins, right, by location in the simulation volume, and each bin could hold any number of atoms. So but we use for cutoff potential for each grid point. We only use these bins partially or fully covered by the RC sphere. That is, if we draw a cutoff potential sphere, then we can see how many bins, right? For this particular, let's say for this particular grid point, we draw that sphere, and then we can actually enumerate all the bins, right? All the bins that are intersected or covered, right, or included by that sphere, and those are the only ones that we need to access for this grid point, to be able to to calculate all the short distance forces. Make sense? Mm-hmm. Okay. So this allows us. So if we sorted the atoms into all this, then each grid point can just use its coordinate, right, and ask, give me all the bins that I should look at according to my sphere, right? And then, so each one of them will find on average about 7 of them, right? So then you have a linear algorithm. It doesn't matter how big your simulation volume is, because every grid point is only going to be looking at its localized atoms. Right? So that's the kind of the first algorithm. So there are 2 things about 2 important terms for this kind of scheme. One is bin size, and one is bin capacity. This is kind of arbitrary, but we define it this way so that when we talk about the computational trade-offs, it's clear which one is which. We'll say bin size has to do with the simulation, the physical dimension of the simulation. Okay, so it's the size of the bin cubes that partition the simulation volume. Okay, so how big a physical space each bin covers. So that's the bin size. Okay. And the bigger the bin size, the more the space each bin covers, and more atoms that will fall into each bin. And the way to think about it is that the bin size is how aggressive you're bundling the data, you're coarsening the data, okay? Because you tend to generate bigger bundles, right? When you include a bigger space in your bin, in each bin, you tend to bundle more of those atoms inside the bin together. And whenever one of them gets accessed, the rest will be accessed. So they all have the same fate in terms of memory accesses. Okay, it doesn't mean that they will all contribute. Some of them will be rejected, some of them will not. But every thread, when they look at any of, if the thread looks at any of the items in the bin, it will also look at the other items in the bin. Because that's the only way each thread is going to be accessing memory. Okay, so this is also something very, very important for you to begin to make a transition. When you look at the dense matrix computation, especially the GEM computation or even the stencil computation, we did not mess with the memory data. Okay, we assume that the memory data, comes in. The memory data is kind of in the regular array, right? And then we do the tiling. We access the memory data into our on-chip memory, and we try to organize our on-chip memory in a way that is efficient, and we try to minimize the use of on-chip memory. But we didn't really mess much with the in-memory, the global memory data. We started to do a little bit of that when we talk about the transposition of one of the matrices in C or Fortran, right? So that's when we started to mess with the in-memory, the global memory data, because we needed to have that so that we can actually load do the register, load the register contents more in a coalesced way. So that was kind of the beginning of this kind of slippery slope. Here, we're actually doing some very significant messing around with the input data. We're taking the atom array, right? So you can think about atom as a simple atom array, and then we create a multi-dimensional, a multi-dimensional of small arrays, and each array will be containing several atoms, and we're putting the single atom array into these, one of these, entries of that multi-dimensional array, right? So this is a major messing around, and we're going to see even more messing around later on. People get more and more aggressive. And if you talk to any of the very experienced data, the experienced senior computational people in any of these top companies, they will tell you the most important part of their job is to figure out how to organize data, okay, for the various computation, including parallel computing, including distributed computing. They're very senior people in Google, in Microsoft, and so on. Their single most important job is to figure out how to organize their data in their databases, in their in their storages, and so on, so that they can handle these distributed computing and parallel computing in a reasonable way. Okay. So sometimes people say is the data stupid? Okay. If you really are serious about handling very large amount of data fast, you have to think in terms of the organization of your data. Okay? So this is the kind of the real beginning of it. The bin capacity is less of a physical concept, but implementation concept. The bin capacity is the size of that little array that you allocate. You can allocate, 5 elements per small array. You can allocate 20 elements in that small array. What's the basis of your calculation? It's problem dependent. So, the number of atoms that can be accommodated by each bin in the array implementation. We do this all the time, by the way. We all have, in this situation. The airline companies have a very, very hard job. They have these very expensive planes. Each plane has a certain number of seats, right? And so, during, most of the time of the year, these planes are not full, right? Until the day after Thanksgiving, or until 2 days before Christmas. Then all these planes are full, and people are still waiting to get on the plane. So you see my point. My point is you have these fixed capacity, vehicles, fixed capacity, instruments and so on, that we have to determine a certain size, and that size is not going to be good enough for anything, but it's a compromise. Okay, you don't want to waste too many seats during the low season, and you don't want to have too many people who cannot get on your flight in the high season. And sure enough, you have the mechanism, during right before Christmas or right after Thanksgiving, you will hear this announcement. We have an oversold situation. And so we're offering, something like $1,000 for each person who have flexible travel arrangement, right? And that's essentially to deal with the exceptions, because the airline people need to also deal with a very bad, uncertainty. That is, people sometimes don't show up. Okay. Think about this classroom. When you registered, this classroom size was the limit. Okay? So we cannot sign up any more people because every seat of the classroom is supposed to have been taken. And the fire marshal assumes, that everyone will show up at every lecture. I see some empty seats, right? So we should be able to oversubscribe to these courses, but the fire marshal will not allow us. Okay, and so the airlines, because they're in the business of making money, they don't want to have these situations, so they oversell. Okay, and then when everyone shows up, they do the $1,000 thing, right? Some airlines, terrible ones, do the dragging thing. So, but that's all because you have a fixed capacity, right? Fixed capacity, and then you need to deal with the variations. Does that make sense? Okay. Now we see how we deal with it. Sometimes we do the dragging thing too. So the capacity of these atomic arrays need to be balanced. Too large, there are too many dummy atoms in the bins, in bins that are in the kind of the sparsely sparsely populated areas, and if it's too small, some of the atoms will not be able to fit into bins, right? You have the densely populated areas, then you have too many atoms, that you cannot fit into your smaller bins. So to target bin capacity to cover more than 95% of the atoms, you do a careful study about the density of your atoms, and you say, if I design the bin capacity to be, let's say, n, then I will cover the 95% of the bins will have sufficient space for the atoms, and 5% of them will not have enough capacity. And then we do either the bribing thing or the dragging thing, okay, for those bins. Does that make sense? Okay. So the CPU places all the atoms that do not fit into the bins, right? The CPU will sort, or the GPU in some cases could sort, but it's a little bit trickier. So you sort these atoms into the bins, and sure enough, 5% of them will have trouble. So 5% of the atoms will not be able to go into the bin because there are already all these atoms in the bin. So it's already full capacity. So then we just put it into an overflow bin. Okay, so we say this atom cannot go in because it's already occupied. So I put that into an overflow bin. Okay, that overflow bin will be eventually processed by the CPU sequential algorithm, and to calculate their contributions to the energy grid by this point. So the CPU will do a sequential scatter algorithm to take these atoms and then just essentially patch the value into the energy grid after the GPU finishes with the 95% of the atoms. And so the CPU and GPU can do potential calculations in parallel, okay, or in serial if you want. So the bin design, so then let's look at some of the trade-offs that we need to deal with in bin design. So we have a uniform size and uniform capacity, right? It's both uniform. Size, they all cover the same space. Capacity, they all have the same number, right, of entries. So they allow the array implementation, and so we can do what we call the relative offset list approach to simplify runtime identification of the relevant subparts of the atom. So this is about neighborhood offset list, and we're going to see how that works. And then it's easy to translate from spatial coordinate to bin index. Whenever you have an atom who has a spatial coordinate, you can easily translate that into the index of the bin that contains that atom, right? So that's why these things are very, very simple. And bin sizes could be should be big enough to contain significant number of atoms in each bin, and the cutoff will screen away atoms that should not be processed. However, the performance penalty, there can be performance penalty if too many are screened away, and if you have too many in the overflow bin, then your performance start to suffer. So this brings us, to a very important concept of work efficiency. Whenever we coarsen the data, whenever we create these bundles, we start to have, this issue of work efficiency. Because remember, every time a thread accesses any of these atoms in that bin, you access all the other atoms. So you could be looking at some of the atoms that if your cutoff distance may be only the cutoff sphere may be just intersecting with part, right, of that bin. So some of the atoms are actually outside the distance. But because you always bring in the whole bin's worth of atom when you access memory, and when you inspect the atoms, you will do some extra work because some of these atoms are brought in. Okay, so the thread block examines item to the up to the cutoff distance, and to be even more of an issue, we're looking at a GPU kind of code where we're going to have let's say a thread block to process all the grid points inside a bin size, right? So let's say this is one of the bins. It will contain, let's say several atoms, but it also contains a large number of grid points, right? So the point of the gather algorithm is for each thread to compute one or more of these grid point values. So we're going to be using a thread block, okay, to compute the grid values for all the grid points inside one bin. So this actually, creates a little bit of a problem, because if you look at the grid points in the middle versus the grid points at the corners, when you draw a sphere, a cutoff sphere for this point versus this point, they are not covering the same thing. They cover slightly different bins, right? Because this guy requires the sphere to be pushed in that direction a little bit. So essentially we need to create a sphere that satisfies the need for everyone in that bin, okay, for the grid points. So this means that we're going to be fetching some of the bins. For example, this guy, the reason why we're fetching this guy is because of this corner point, and this guy couldn't care less about these guys, right? So on the other hand, because we're using a GPU programming paradigm, and we're fetching these atoms for examination by all the points in the thread block, because of the thread coarsening, we will have some threads that will have fewer useful atoms than these threads, right? So the strategy, but the good thing that we gain for this strategy is that we're going to be fetching all the atoms in this bin into the shared memory, and then all the threads can just access the shared memory to determine the distance, right? To determine the cutoff, whether it's within or outside the cutoff, so that the memory accesses can be significantly reduced because all the threads can share that content of the shared memory. You only need to bring in each bundle once, and they can be used by more than 100 times by the hundreds of threads, right, in that thread block. So that's why it's important that this bin is big enough to have enough grid points that you can have enough threads, right? But you don't want to have it too big, because if you have too big, then this kind of effects start to take it, so that you bring in too many of the atoms that are not relevant to parts of the threads. Does that make sense? So this goes back to one of my favorite things about that I usually talk about in 408. When airlines serve, they used to serve food, right? So when they still serve food, I miss those days. So when they serve food, they give you a tray, right? The tray will have everything, the fork, knife, the spoon, and pepper, salt, right? Everything that you might be able to ask. They don't ask each of you, do you want a spoon? Do you want a fork? Do you want to have the knife? Pepper? No pepper? They just give you a tray, right? So you think about that as the bundling, okay? Everything in that tray is bundled together. They're all served to every person, but some people only want to use spoon. Some of them, people only want to use knife. Some people want 2 packs of pepper, but bad luck, right? You don't only have one. You can beg the person next to you if you want to have two packages of pepper. But that's bundling. You think about it. That's exactly coarsening. Okay, all these things are coarsened together and they're served to in one shot, and you don't have that customization. And this allows the airline to serve you fast, right, during the flight. And so here, the spheres has to be big enough to cover the things for all the grid points, including all the corners. And then there will be some level of divergence, because by the time the threads actually, so you bring in the data into the shared memory, and then all the threads will examine the data on behalf of the grid points, and that's when the real distances are calculated, right? The real distances are calculated, and some of the distances are too big, right? So then that's a wasted test, right? On the other hand, some of the threads will say, oh yeah, it's within my distance, so I'm going to make the contribution. So there will be divergence, right? Some threads will succeed the test and make the contribution. Some threads will fail the test and then say, okay, I'm not going to do the computation. And so that gives us the divergence. And so we would like to be able to minimize that divergence as much as we can. And I'm going to show you some interesting the little tricks that people play in these kind of software. And not all the grid points processed by a thread block relate to all the atoms in a bin the same way. So, for example, here A is within the cutoff distance of this guy, but not the cutoff distance of this guy, right? So I already said it multiple times. So you can create either a single sphere that is the super sphere, right? That's the super sphere of all the small spheres for all the grid points, and it's called a super sphere. You can do that. Or you can actually just draw individual spheres. Okay, so you draw all the individual spheres for all the grid points and make sure that you collect all the bins that are touched by at least one of the spheres. Right. You can do it either way. Okay? You see what I'm saying? Yes. You don't have to create a super sphere, right? You can just say, as far as this grid point is concerned, I draw the cutoff sphere, and then I collect all of them, and then because the next one, I draw the sphere, and I collect any additional ones, right?
Okay.
So in the end, I will have a superset for everyone, right? But either way, this is a fairly time-consuming, fairly hard, computational geometry problem. So that's why these things are almost invariably pre-computed. They're almost never done on the fly. Okay, and I'm going to show you, how people do that in next slide. Oh, wait. There's something I also want to say. So basically, if you look at the, all the things that will be collected for a thread block, they kind of look like this. Okay, they look like a kind of a, the zigzag shape, with some of the corners probably cut off because they're too far away from any of the grid points, right? So you get something like, they're mostly symmetric, right? So it's kind of weird stuff. So that, because it's computationally very expensive to figure out whether a particular grid, bin should be involved in a particular computation of a thread block, we usually use what we call the neighborhood list, offset list approach. And this approach only works for uniform binning. Okay. For non-uniform binning, you need to use something different. Okay. So this is part of the reason why we use uniform binning as much as we can, because it simplifies things enough that a lot of the simpler schemes work and your software is reasonably simple. As soon as you go into the more complex, spatial sorting techniques, you start to introduce more and more complexity into the various aspects of your computation. So the neighborhood offset list is a list of relative offsets enumerating from the bins that are located within the cutoff distance for a given location in the simulation volume. So let's say if for this guy, I'm going to have a neighborhood offset list that enumerates the offset of all the bins that should be collected. So here I'm showing a kind of a two-dimensional case, right? So if you have a two-dimensional case, let's say I draw a circle, and then I know that I need to cover all these bins other than just the corner ones, right? Okay. So what I do is I call this 0. I call this point 0 coordinate, right? So this bin is 0, 0. And then from the bin point of view, if I just give index into each bin, this is 0, 0, and this is going to be 1, 0 in the x dimension, 2, 0, and this is going to be 0, 1, right? 0, 2 in the y dimension, right? So I'm going to just say this one, for example, that I could have -1. This is -1 and -1. So this is a -1 here. So I can just enumerate all the bins that will be, intersecting or included by this circle for the two-dimensional case. So I just generate a list of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I generate a list of 21, the bits that I need to process for this particular one, right? So, I'm showing this for one point, but you can think about this as this could be a super sphere, right? For all the grid points inside this thing, right? Or you can be drawing all these, individual exact circles, right? And then just take the superset, right? The superset of all the bins involved by all those circles, right? So this gives me the list. But why is this list good? Because this list is offset. So this can be applied to all the bins, right? So I can easily apply this list to this guy by adding everyone by 0, 1, right? So this gives me the next slide. So let's say, you know, if we have the middle, the center point is 0, 0, I generated this offset list, right? So if I apply this to any point, any of the you know of the bins of grid points, that is x, y, right? It could be 1, 0 here, right? It could be 1, 1, -1 here, right? So say x, y. All you have to do is you just take that same list and add x and y to all the coordinates, and then you can find all the bins. So this is a very, very simple thing for all the thread blocks to be able to immediately identify all the bins that need to be fetched for the threads inside that bin, inside thread block, right? And this can be pre-computed and then just portably used across all the thread blocks, right? And this is, this makes everything very, very simple. So this is the pseudocode that we have. So for each atom in the simulation volume, we take the atom's address, right? And then we divide it by the bin size, and that gives us the index of the bin. So, for one dimension, it's very, very intuitive. One dimension, you have, the bin size is the one-dimensional length of your bin, right? So you take the distance, the real address, right? The simulated physical address, and then you divide it by the size of each bin. You can get the bin index, right? For two-dimension, it's actually not that bad. So you take the x, y, z, or three dimension. You take the x, y, z coordinate. You divide by the the bin size in each dimension, right? And then you do a row major layout of your linear thing, and then you can just calculate the row major layout linearized index, and then you put it in, right? So it's not that difficult. And then the second one is to generate a neighborhood offset list. So for each cube or each bin, right? Each cube covered by the bin. You, from negative cutoff to the positive cutoff distance, you enumerate, right? If the distance of this is smaller than the cutoff, if any of these aspect is touched by the sphere or covered by the sphere, then you add it to the list, right? This is a very simplified thing. It's actually a lot of computational geometry stuff to test it. But since you're only doing it for once before you do the simulation, it's okay. And then you do the computation on the GPU. So for each point in the output grid, okay, for each point in the output grid, this is inside the thread block. So the index of the bin is the point address divided by the bin size. So essentially, for each of these offset in the neighborhood list, you fetch all the atoms in that bin into the shared memory, and everyone use the shared memory to fetch the charge, the distance, the XYZ coordinate, test whether it's inside its own, the distance is smaller than the cutoff distance, and if so, if it's within cutoff, you accumulate. If not, you don't. That's where the divergence will be. I'm going to, so I'll cover a couple more points, and then we'll come back next Tuesday. So, in terms of performance, this whole algorithm has a total amount of work for the algorithm is order n times n prime, where n is the number of output grid points, right? N is total number of grid points. And n prime is the average number in the neighborhood offset list, right? It may be a little bit more than 700 because you're actually fetching a bigger portion part than just a cutoff sphere. It's a super sphere, right? So it may be 1,000, it may be 2,000, but it's fixed. Okay, it's still bounded. So in general, n prime is small compared to the number of all the atoms. So it works well if the distribution of atoms is uniform. So I'm going to cover this one, and then we're going to restart with this one next time. So in order to have accurate enough simulation, you usually need to have the lattice spacing to be an order of magnitude smaller than the cutoff distance. Okay, the intuition is that you need to have enough resolution, right? So if your cutoff distance is about 10 angstrom versus 12 angstrom, you want to have your cutoff distance to be, somewhat, less than maybe 1/10 of the of the cutoff distance, so that you can have accurate representation of your field, your electrical potential field value. So for this case, we typically will have 0.5 angstrom lattice spacing. But obviously, this is just one application example. So basically, if we have a 4 angstrom cube bin, okay, so 4 angstrom cube bin, bin size, then we will have in each dimension 4 divided by half will give us 8 grid points. 8 grid points in each dimension. So this gives us 512 grid points in each of these bins. Okay, each of these bins. About 512 of these grid points, and then if we coarsen the thread so that each thread will calculate 4 points, then we use 128 threads. If we don't coarsen, then we have 512 threads. If we coarsen by 2, we have 256 threads. So there are at least a decent number of threads here. But the interesting thing is that if you look at the efficiency, only about 34% of the examined atoms are within the cutoff distance. Okay, so this number was actually a little bit surprising to me when I saw this number the first time in 2012. So, 2010. So basically what this thing is saying is that when you fetch one of these bins, and when all the threads examining these atoms from the bins, only about 1/3 of the atoms will be actually contributing to each. If you look at each point of calculation, about 1/3 of the test will succeed, and about 2/3 of the test will fail. And this means two things. One is the supersphere is probably quite a bit bigger than the real cutoff sphere, right? So these people were brought in for this guy, but not for that guy, right? That's one part. And the other part is there's still a non-trivial number of, even if the sphere is exact, because of the data coarsening, we still have a very significant number of these bins that are only partially included, right? So when we fetch those, we will still have these atoms fail, but these atoms will succeed. So the combination of these two factors, when we have an exact sphere, we still will have all these partially covered, the bins, but because we're doing data coarsening, right, we're bringing in these, and also the supersphere. When we do the computation coarsening into thread blocks, we have additional, we bring in the supersphere worth of spins. So these two combined together give us about 2/3 of the atoms that are actually kind of not succeeding. But they're not the same 2/3, okay? And the thread on the upper left corner and the thread on the lower right corner will have very different 2/3 of the atoms that fail. Does that make sense? Yes. Okay. So the output tiles and the atom bins need to be as close to cube as possible to minimize efficiency. That is, you don't want to have this thing to be like a rectangle, because when you have a rectangle, you will start to have even bigger super spheres and so on. And also, you want these bins, you want these bins to be not too big, because when the bins are big, the quantization effect is going to be more, it's going to be more pronounced. But you don't want the bins to be too small, because if the bins are too small, every time you bring some, you're not going to have a lot of, atoms, grid points inside the bin for the thread block, right? So these are the engineering factors when you design this kind of parallel software. At some point, simplicity versus complexity. When you have the certain size constraints, if you make things too big, it may be inefficient. But if you make things too small, you may not have enough parallelism, and so on, right? So these are the things that will essentially, bound the solution space. This is the reason why we published this, 2012, 2008, 2012 CGO paper about the search space. How these search space are defined in GPU code, and that won the CGO, the CGO Test of Time paper award last year. Right? So, some of these things, once we start to teach the material, we organize it, it becomes very clear, right? But then back then, it was a award-winning paper, less than 10 years ago. Right? So this is how fast these things advance. So, this is, if you look back, same thing with the, joint register and shared memory tiling. 10 years ago, it was world record-setting, magic piece of software. Today, for anyone who can take in 508, piece of cake. Right? But that's how we make progress in our research. Make sense? Okay. So I'll see everyone Tuesday. Very important. Try to finish MP2 by Sunday if possible. If you really need more time, we'll give you more time. But these things are, that we just want to make sure that everyone is, we don't drag on for too long, so that you can finish all the subsequent, assignments. Okay? So see you on Tuesday.